John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
Now, the next topic that we're going to discuss before wrapping up with Lewis acids, the definition of Lewis acids and bases, is the relationship between molecular structure and acidity. Now, overall, the overriding principle in determining the relative acidities of uncharged organic acids is the stability of the conjugate base anion, A-. Now, this results from the loss of a proton, and so the more stable the anion, the greater the acidity of the acid HA. So again, written out here, the more stable the anion form, the conjugate base, the greater the acidity of that conjugate acid form. So in this section, we're going to talk about 5 different ways to stabilize this anion. The first is to have the negative charge on the most electronegative atom. The second is to have the negative charge on a larger atom. The third is to delocalize the negative charge, or those electrons, as much as possible. The fourth is to spread that negative charge onto electron withdrawing groups by the inductive effect. And then finally, to have the negative charge in an orbital with more S character. And so we're going to now look at each of these one at a time. Now the first one relates to the relative acidity of a species with electronegativity. So the relative acidity within a period of the periodic table is related to the electronegativity of the atom and the anion that bears the negative charge. So the greater the electronegativity of this atom, the more strongly its electrons are held, and therefore the more stable the anion is. Conversely, the smaller the electronegativity of the atom that bears that negative charge, the less tightly its electrons are held, and the less stable the anion is. So as an example, if we look at here methanol, methylamine, and ethane, we can see here we're looking at this change in the atom. So we have oxygen, nitrogen, and carbon here. And so all of these atoms lie in the same period of the periodic table. We can see that there's an increase in the acidity of these species going from the bottom to the top based on the electronegativities of these atoms, because those are the ones that are going to be bearing the negative charge. So methanol is the strongest acid, methylamine is the middle, and then ethane is at the bottom. So the methoxide ion is the weakest conjugate base, and the ethyl anion is going to be the strongest conjugate base. So not surprisingly, these pKa values increase as you go down here. Now what about atomic size? So to illustrate how the acidity of hydrogen acids varies within a group, or within a column of the periodic table, let's compare the acidities of methanol and methane thiol. So we saw previously that the pKa of methanol is about 16. So now let's estimate what the pKa of methane thiol would be. So the pKa of hydrogen sulfide, H2S, can be found in most tables, and it's given as 7.04. So if we assume that the substitution of a methyl group for a hydrogen makes only a slight change in acidity, then we can estimate that the pKa of methane thiol is about 7. Therefore, methane thiol is the stronger acid, and methane thiolate ion is the weaker conjugate base. So if these two acids were mixed to react with one another, we'd have the methane thiol all the way on the left-hand side as the stronger acid. Our pKa is 7. The methoxide ion is the stronger base. The methane thiolate ion is the weaker base. And the methanol, which has a pKa of 16, is the weaker acid. And so that's why the equilibrium here, the position of equilibrium, lies to the right-hand side, because we have the stronger acid reacting with stronger base to give the weaker acid and weaker base. Now, getting back to the atomic size, the relative acidity of these two hydrogen acids, and in fact any set of hydrogen acids within a group of the periodic table, is related to the size of the atom that bears the negative charge. So size increases from top to bottom within a group because the valence electrons are in increasingly higher principal energy levels. Now this means that they are farther from the nucleus and they occupy a larger volume of space. Now because sulfur is below oxygen, it is larger than oxygen. Accordingly, the negative charge on sulfur in the methane thiolate ion is spread over a larger volume of space. It's more delocalized. Therefore, the CH3S- anion is more stable. We see the same trend in the strength of the halogen acids, so HF, HCl, HBr, and HI. So these increase in strength from HF being the weakest to HI being the strongest acid. So of their anions, the iodide ion is the largest. Its charge is delocalized over the largest volume of space and therefore is the most stable. The third relationship between molecular structure and acidity is that the conjugate base, or the anion, the negatively charged form of an acid, can be more stabilized by delocalizing the negative charge as described by resonance contributing structures. Now this is most readily apparent in carboxylic acids. So carboxylic acids in general are more acidic than alcohols, mainly due to this delocalization as a result of the two resonance forms that you get of the anionic conjugate base form. The fourth way to stabilize the anion form is through the inductive effect. So this is the polarization of electron density of a covalent bond caused by the electronegativity of a nearby atom. So we can see an example of the inductive effect in alcohols in the fact that an electronegative substituent adjacent to the carbon bearing the OH group increases the acidity of the alcohol. For example, if we look at, on the left-hand side, ethanol, and on the right, we have 2,2,2 trifluoroethanol. We can compare their pKa values at 15.9 for ethanol, and for the trifluoroethanol, we have 12.4. So the latter species, the one with the trifluoro group, is more acidic because of these electron withdrawing groups of the fluorines as a result of this inductive effect. So what that means is that the anion form of this acid is considerably more stable than the ethoxide ion. So we can account for that increased stability in the following way. So fluorine is more electronegative than carbon, so 4.0 versus 2.5. Therefore, the carbon-fluorine bond has a significant dipole. Now this is indicated by these partial charges, partial negative charges on the fluorines, partial positive charge on this carbon. Therefore, there's an attractive stabilization by the interaction of the negatively charged oxygen and the partially positive charge on the carbon that bears the fluorines. Now this results in the stabilization of this anion. Now stabilization by this inductive effect falls off rapidly with increasing distance of the electronegative atoms from the site of the negative charge. So that even with the addition of two additional methyl groups in between these two carbon atoms, the pKa difference between ethanol and that species is not really going to be that different. Finally, the anion form, A-, can be stabilized by having the negative charge in an orbital with more S character. So to see the effect of hybridization, we consider the case of two or more conjugate base anions, each with the same charge and same element bearing the charge. The only difference is the hybridization of the atom that bears the negative charge. So the acidity of a hydrogen bound to a carbon atom of an alkane, an alkene, and an alkyne is of special importance here. So we can see in the chart given that alkynes have a lower pKa value than alkenes or alkanes. And we can account for this greater acidity of alkynes in the following way. So the lone pair of electrons on a carbon anion lies in a hybrid orbital. So it lies in an sp orbital for an alkyne, an sp2 orbital for an alkene, and an sp3 orbital for an alkane anion. So if we look at the percent S character here, in an sp orbital, this has 50% S character. An sp2 orbital has a third, or 33% S character, and an sp3 orbital has only 25% S character. So electrons in an S orbital are lower in energy than those in a p orbital. That is, they are held more tightly to the nucleus. So the more S character that an atom has, the more electronegative it's going to be, and therefore the more stable its anion. So in other words, the more acidic a hydrogen bonded to that atom is going to be. So of those three types of compounds, the carbon in an alkyne, which is sp hybridized with 50% S character, is going to be the most electronegative. Finally, we're going to switch gears a little bit, going back to our different definitions of types of acids and bases, to wrap up with the most general definition of an acid and base, the Lewis definition. So this general theory includes the groups of substances that are not included in the Bronsted-Lowry concept. So according to the Lewis definition, an acid is a species that can form a new covalent bond by accepting a pair of electrons, where a base is a species that can form a new covalent bond by donating a pair of electrons. So, in this general equation, the Lewis acid A accepts a pair of electrons in forming a new covalent bond and acquires a negative formal charge. The Lewis base B donates the pair of electrons and acquires a positive formal charge. Now, although we speak of the Lewis base as donating a pair of electrons, it's not exactly accurate. So donating in this case does not mean that the electron pair under consideration is removed completely from the valence shell of the base. Instead, donating means that the electron pair becomes shared with another atom to form a covalent bond. Now, in this example, if both reactants are equally but oppositely charged, a Lewis acid-Lewis base reaction will result in the formation of a new covalent bond in which the product has no charge. And so the example here is that of the carbocation, the Lewis acid, with the bromide ion, the Lewis base. Now, the Lewis concept of acids and bases includes proton transfer reactions. All Bronsted-Lowry bases, proton acceptors, are also Lewis bases, and all Bronsted-Lowry acids, or proton donors, are also Lewis acids. So let's look at an example of this, of a reaction between a Lewis acid and a Lewis base that does not include the transfer of a proton. So here we have BF3 reacting with ammonia, NH3. So BF3 has an empty orbital in the valence shell of boron, and this is the Lewis acid. NH3 has an unshared pair of electrons in the valence shell of nitrogen and is the Lewis base. In this example, each of these atoms takes on a formal charge. The resulting structure, however, has no net charge, as you can see.